All right, hello everyone. Welcome back to the hottest seminar. And this week we have Martín Escardó from the University of Birmingham telling us about injective types.
Thank you, Carlo. Thanks for the invitation as well. It's nice to be here. So I'm going to talk about two pieces of work on injective types. So one I published quite a while ago in 2021. But then more recently, I've been doing some work with Tom de Jong, which is actually it's all formalized in type topology in Agda. So type topology is a library based on the univalent foundations that has all sorts of things, but in particular, it has a lot about injective types. We're still writing a paper. It turns out that, in my opinion, it's more difficult to unformalize mathematics than to formalize it when you want to write it down in a paper. Okay, so I need to click a button because Zoom is pestering me to press OK. Here we go. So injectivity of types is about the extension problem. So you extend the type to a type Y, so using an embedding, and you have a function into D. So I'm going to use D actually for the injective spaces. And you want to extend it to the larger type. And so there are several equivalent definitions of embedding. In this talk, it will be convenient to adopt the one that says that the fibers of every point are propositions. And so I'm going to say that D is injective if for every F I can find an F that extends F along J. And I'm going to say, so this is actually existence, so truncated sigma. And I'm going to say that D is algebraically injective if you can actually, there is a designated F. So you can actually, there is a procedure that finds uniformly F bar, the extension from F. And I'm going to use division notation for it because if you think of composition of multiplication, so it's the inverse of composition. And so let's begin by first looking at what happens in the classical world. So the principle of excluded middle, so which means you're in a Boolean topos, is equivalent to saying that the algebraically injective types are precisely the pointed types. So in a Boolean topos, the injective types are a little bit boring. They are just all the pointed types. So it becomes more interesting in arbitrary topos. And similarly, the injective types, instead of being the pointed types, if excluded middle holes, are precisely the non-empty types. Now, an axiom that some people actually adopt in this community, but we are not going to adopt, but I'm nevertheless going to discuss in the first few slides, is propositional resizing. So for example, the Unimath project initiated by Vladimir Vevovsky uses propositional resizing. And so then things actually becomes much simpler to understand. So for example, so injectivity is actually equivalent to the propositional truncation of algebraic injectivity. And that's not because we truncate the sigma, but the quantifiers are actually, so for every F and J, there is something, so you actually can put the truncation way outside. So this is a kind of a choice that just holds, you can prove it. And then there are some characterizations of the algebraically injective types. For example, they are precisely the retracts of types of the form X R of U when U is a universe, or an exponential power of universe. And also there are particular cases of this. So for instance, the algebraically injective sets are precisely the retracts of power sets. And actually this mimics the classical case of one topos theory, where this is also was known to be the case. But we can generalize a little bit. So the algebraically injective n+1 types are the retractive types of the form X arrow U, where U is a universe of n types. Yeah, and this is a generalization of A because the power sets are just function types of this form, where U is the type of proposition, so -1 types. Feel free to interrupt me if you have any question. We don't need to wait until the end to sort out your doubts.
Well, actually, I have a question, which
Yes.
does that generalize any further to other sorts of like modalities or whatever?
I don't know. We haven't investigated this yet, but this may follow from other things that I'll discuss later. Okay.
Yeah.
So another characterization is that the algebraically injective types are precisely the underlying types of the algebras of the partial map classifier monad. So a concrete description of this monad, or at least the functor of the monad, is so I call it L because I come from a community domain theory that calls this lifting. So the lifting of X is the type of partial elements of X. So we have a proposition and a function from the proposition to X. Of course, when the proposition is the 1-point type, this is just an element of X, or you can say a total element of X. And so the algebras of this monad and the algebraically injective types are in one-to-one correspondence. You may think to ask whether there is an equivalence of types. I will discuss this in the very last slide. And also with propositional resizing, something funny happens. So any universe is a retract of the next universe. And but when we don't have propositional resizing, a lot of things change. So one thing is we're forced. So in the previous discussion, you can see that I hardly mentioned universes, but now when I draw propositional resizing, I need to keep track of the universe levels. So for instance, if you want to talk about the injectivity of D, which is in some universe W, we're going to say that it's UV injective if for every X in the universe U and every Y in the universe V and every embedding, the extension problem can be solved. Now, coming back to when you do have propositional resizing, what happens is that actually the injectivity is universe independent. So D is injective with respect to universe U and V, if and only if it's injective with respect to any other two universes, U prime and V prime. Okay. Now, from this point on, I choose for this talk well, firstly, I'm not going to assume propositional resizing, and I'm going to work exclusively with algebraically injective types, and I'm going to just call them injective, but be warned that these are algebraically injective types that we're talking about. So one of the simplest example of an injective type, but also the typical example, as we'll see later in some sense, are the universes. And there are multiple ways in which a universe is algebraically injective, because algebraic injectivity is data, and so there are many ways in you can find the data, but there are two extreme ways. So one is you can do left can extensions, that's kind of a minimal extension, and the other one is you can do a right can extension. So concretely, so if you have function from X to a universe bigger than U and bigger than V. So I'm using this notation here to indicate that this, kind of the least upper bound of the universes, as you like, if you like. So if you want to define the extension, so you start with Y and that you want to define the function, then you pull it back. So you take the fiber of it, and now you do the sum. And you consider only the first component of the fiber. and then you apply the first component to F, and you sum this. Now, this is a funny sum because it's a sum over a proposition, so it's a sum that has over an index set that has at most one element. Yeah. So classically, this is either empty or inhabited. And so if it's empty, it means Y is actually not in the image of the embedding. And otherwise, you just, it is in the image, and then you just take the same value as X. But of course, the situation is more complicated in an arbitrary topos of what really is going on. And you can instead do the product. So you may notice that when in this extension, when Y is not in the image, then the sum will be empty. But here, when Y is not in the image, the sum will be the unit type. Yeah. So of course, a particular case is that the universe U is injective with respect to U as well. Yeah. But if you try to increase the universe here it doesn't matter much, as we'll see later. But if you try to increase this universe here, you won't succeed. Yeah. So unless you have propositional resizing. So I'm going to consider an axiom which is kind of in between nothing and propositional resizing, which I call it omega resizing. So omega not resizing. So you take the type of not stable propositions. And so this lives in U plus. And this resizing axiom says, well, actually, this type which lives in U plus has an equivalent copy in U. And now this is actually not provable or disprovable in univalent type theory. And this follows by two different papers, one by Michael Rathjen, which discusses the proof theory of inductive types and univalence. And basically, what happens is that if you assume this, you increase the strength, the so-called proof theoretic strength of the system. And in the other direction, Andrew Swan gives a model and cubical assemblies that actually validates this axiom. So this axiom may or may not hold in different models. And here is the no-go theorem, which justifies this claim here that I cannot replace this U at the upstairs for something bigger, because then the injectivity will fail. Will fail in the sense that if you have that any type D in the universe U is injective with respect to a universe bigger than U, then this omega not resizing must hold. Yeah. So one way to summarize this is that there are no small injective types. Yeah. So, for instance, if you take, let's say, D to be in the first universe, and then you want it to be injective, well, you won't succeed. Yeah. Unless you have resizing, of course, as I said before. Okay, then there are some standard things. So I'm going to go very quickly over these standard things, but they're useful. So if D is injective, then a retract of D is also injective, D prime, because if you have a function, then you can compose it with a section and then extend it using the injectivity of D, and then you can compose with a retraction, and then you get the extension. And similarly, another useful fact is that if you have a lot of injective types DI, then the product is also going to be injective, and then you just do the extension pointwise, basically. So there is nothing very clever here. And another fact is that also a standard fact about injectivity. Every injective type, so if this injective and if it's embedded into any type whatsoever, then it must be a retract of that type because you can consider the identity. So every embedding of an injective type into any type is a section. Let's see how fast I'm going here. So an interesting embedding is the identity type former. So if you consider the map that embeds X into this function type that sends X to Y and then X equals Y, this is an embedding. So that's a kind of a Yoneda embedding, if you like. And actually, this is not just a mere analogy. It actually is quite precise. And combining this with this fact here, so you have that if D in U is U plus injective, then D is a retract of DR of U. Because you use the identity type to embed and then this, okay? Now, of course, this theorem can be proved without resizing, yeah? But the problem is to fulfill the hypothesis that D is a U plus injective, because actually the no-go theorem prevents you from having that. So you can only have this hypothesis if you actually did have resizing. So this is, although this is true, is not very useful unless you have resizing. And so here are lots of examples of injective types. Well, it's not surprising that they live in a successor universe, because we know that, you know, in the base universe there cannot be any injective by the no-go theorem. So we have to consider a successor universe. And so one of them is the type of propositions in U. Another one is the type of n-type, the ordinals in U. And also said before, but I didn't write it in this slide, you can generalize this 0 to the type of sets is also injective, the type of one types injectives, the type of n types is also injective. Then some people investigated models of material set theory in univalent foundations. And then we have this iterative sets and iterative multisets. And the type of those are both injective as well. Another example is the type of pointed type. So this is injective. More interestingly, so a lot of mathematical structures are actually, when you put them together, they form injective types. So the type of magmas, infinity magmas, pointed infinity magmas, monoids, groups, and many more things, they are all injective. Another example is if you fix any type X in U, and then you consider the type of partial elements of X, this is also injective. And another class of examples, with two examples given here, is soup lattices and pointed, directed, complete DCPOs in U plus are also injective. So remark here is you can ask, well, what about soup lattices in U rather than U plus? Well, in his PhD thesis, Tom de Jong showed that without propositional resizing, you get a similar no-go theorem. So if there is a small soup lattice, then omega not resizing holds. So, and this are some examples. And
what did the last point mean? The carriers of these
well,
things?
I mean, yeah, just any type which admits the structure of a soup lattice is itself
Right.
Injective,
Okay.
or the structure of a pointed DCPO. And here are some counter examples. So let's define weak excluded middle. So for every proposition P, either not P or not P. So this is actually equivalent to De Morgan's law. Peter Johnston investigated this in papers and in his book, The Elephant. So for instance, the same thing that is there is true here. So for example, if the Booleans 1 plus 1 are injective, then weak excluded middle holds. This second example is not in Johnston, but if you told him, he would tell you that he knows that. So if you start, types that people consider in computability theory, so start from n and then start iterating function spaces. So these are called the simple types of system T, for instance. And these, none of them, if any of them is injective, then weak excluded middle holds. If the type of Dedekind reals is injective, then weak excluded middle holds. That's a type that I use frequently in my work, the 1-point compactification of the natural numbers. If it were injective, then weak excluded middle will hold. And also any type that has an apartness relation. I'm not going to define it now, but if you don't know this, you can ask me later at the end. So any is a concept that constructive mathematicians consider as a strong notion of not being equal. If any type which has an apartness relation and 2 points apart cannot be injective unless weak excluded middle holds. And also any type that can be decomposed into pieces is not injective unless you have weak excluded middle. And so now we're going to consider another kind of counterexample. So there is this funny axiom that says that all propositions are projective. So it's like the axiom of choice, but restricted to families indexed by propositions. When the type family is a 2-point type, this is known as the world's simplest axiom of choice. So Foreman and Shetrov gave a model in which it's a topos in which this doesn't hold. And this actually was to answer a question by Richman, Fred Richman, the constructive mathematician. So he was trying to look at the fundamental theorem of algebra constructively. And then he came across this world's simplest axiom of choice to be able to actually do it. And then they gave a counter model to that. So why did I introduce this? Because if the type of inhabited types instead of pointed, so I told you before the type of pointed types is injective. But if the type of inhabited types were injective, then all propositions would be projective. And in particular, the world's simplest axiom of choice would hold. Yeah, so not in all toposes, this type of inhabited types is injective. And now here is an example related to the counterexample. What if we replace inhabited by non-empty? Would you expect this to be injective? I'll say, well, my first expectation would that this would be less likely. But then when we started discussing this with Tom, it became more likely. And actually, the type of non-empty types is always injective in any topos. So this actually gives a concrete illustration of the difference between propositional truncation and double negation. Yeah, that sometimes people think that they are similar, but actually they're equivalent if and only if the topos is Boolean. Okay, so one reason I was interested in injective types, I'm going to tell you in the last slide, but I can give you a preview now, is because I was interested in certain questions on computation. And when you look at types in computation, one thing you try to do is you try to identify lots of decidable properties of this type. But it turns out that injective types have no non-trivial decidable properties. So for those of you who know computability theory, this is a kind of a Rice's theorem for injective types. So Rice's theorem, computability theory, says that certain types that occur in computability theory have no non-decidable, no non-trivial decidable properties. So let's define this more precisely. So the composition of X is a function into the Booleans that has value 0 for one point and value 1 for another point, or equivalently a pair of types whose sum is equivalent to X, and each of them is pointed. And so if an injective type has a decomposition, then again, weak excluded middle holds. And actually, this is an if and only if. Well, actually, I retract this not as false, but because I have to check. I don't remember now anymore. But certainly what I wrote here is true. Okay, so now we try to look at a little bit more about injective. So we know products of the injective are injective, but what about sums of injectives? In particular, what about subtypes? Well, a subtype of an injective type is not always injective. An example was the universe is injective, but the subtype of inhabited types is not an injective type. So one definition of subtype would be a sigma type where the second component is a proposition. It is equivalent to the definition of subtype as given by an embedding. And but here for this theorem, we consider the sigma version. So a subtype D in D, the satisfying property D of an injective type in U plus. We're using U plus because of the no-go theorem. It's going to be U injective if and only if there is a chosen or designated function f from D to D such that P holds for the elements in the image of D. And if P holds, then D is a fixed point of f. And this actually is related to the previous two examples. So for this type of non-empty types, to prove the injectivity, you can use the function f of x, which is not x implies x. And the reason this works is that it is always the case that not x implies x. Oops. Sorry, I did something bad. I need to undo. But if you try to do the same for the type of inhabited types, this doesn't work because if you truncate this, you don't get truth. The truth of this is actually equivalent to propositions that are projective. How am I doing with time? So half an hour. Okay, so that's good. So one way to understand injective types more closely is to look at a particular case, which we call the Flabby types. So instead of having an arbitrary embedding from X to Y, you consider an embedding, well, a map from a proposition into the unit type. And this map is always an embedding. So maybe I can just write the hook here. So we say that D is U Flabby if you can solve the extension problem in this case. So this means that every partial element of D, so a map from a proposition to D, can be extended to an element of D, or for emphasis, we can say a total element of D. So, but if you drop the one here and just consider the element, we can witness flabbiness by a function. I'm going to call it cap, that given a partial element, produces an element such that for every function, whenever you have a point of P, so P is the true proposition, then joining F gives you is the same as evaluating F as P. So that's the commutativity of this triangle here. And now this may seem like a very particular case of injectivity, but actually this completely captures injectivity because, well, one definition is by definition, so injective types are going to be flabby, but this more interesting direction here, so you want to extend F. So what do you do? Again, you start with a Y, you pull it back, take the fiber, and then apply F to it, and then you join it using this extension of, because this is a, let me actually write this for emphasis. I should have written it before the talk. So this is a proposition. So we can do that because the extension of this cap operator here can be applied to any proposition. Yeah. So maybe, yeah. And actually, this generalizes what we did before. So what we did before was exactly that, but for one special case, D was the universe, and cap was either sigma or pi. So that's exactly what we did before. Yeah. And one point of considering flabbiness is that then it becomes much easier to, technically speaking, to prove that things are flabby than they're injective, and then we use this construction here. And so from now on, I'm going to start considering flabbiness instead of injectivity. And let's see if I have to say anything else. Let me make a few remarks. So, so in this direction, we get that if D is UV injective, then it is U flabby. And the reason is that we forget there's a universe here because the unit type lives in any universe anyway. So you forget the V. But now in the other direction, if you look at the universe levels of the construction we did before, what it says is that if D in W is U union V flabby, then it's also UV injective. And now if you convert an injective type into a flabby type and then back into an injective type, you get the following resizing theorem. So that's not an axiom anymore, it's just a resizing theorem. So that if D is U join P and V injective, then it is also U and T injective. So it means that you can actually, well, in this side, it means you can decrease the U. And here it means you can drop the V and take anything smaller than this side here. For the universe of the target of the embedding, yeah. And this is sometimes technically useful in some proofs when the things get very large and you want to make them smaller. Okay, so now we're going to get a little bit more technical, and the point of this is to try to give a sketch of a proof of the claim that, for example, the type of groups is injective. So the type of groups is a sigma type. So we are going to look at the flabbiness of sigma types. And so basically you're faced with this extension problem. So you can consider you have two functions here. F goes from P to X, and G is like this. And you want to know when you can actually extend this to a point of A. And we are going to have two conditions. One is that X is flabby, and the other is I'm going to call it the compatibility data. Before I tell you this condition, so notice that this is only a sufficient condition and is not necessary. In fact, we already had a counterexample in this talk earlier, because we saw that the type of pointed types is Flabby, but then it's easy to see that it is equivalent to the sigma type. So the things in this sigma type such that X is pointed. And this we saw that is not Flabby in general. Yeah. And so this requirement that X is Flabby is a little bit stronger than necessary. But in any case, we don't know of any necessary and sufficient condition. So we only know this. But this is going to be enough for us. So what is the compatibility data or compatibility condition? So because X is Flabby, you can extend partial elements to total elements. And so if you're given an element here in the A of the join of F, then given any P, well, because of the equation that says, well, as soon as you give me any P, sorry, I lost my mouse. So as soon as you give me any P, then the join of F is going to be just evaluate F as that P. So so as soon as you give me any P, this is equal to that, and so I can transport. Yeah, and so this canonical map, if this map has a section, then what happens is that then this type is going to be indeed Flabby. So the two conditions are that X is Flabby and that this map has a given section. And this condition was a simplification of a condition that we considered originally. So the idea was the following originally. So the original idea is say, well, let's use the fact that groups, for example, are closed under products. Yeah. And so basically this condition would say that if we require this to be an equivalence, that will be a closure under products condition. So that was the original motivation. But then realized that having a section is sufficient. And so there is less to check when you want to apply this theorem. But having said that, in all examples, I know this is actually an equivalence. Yeah. And okay, so, but we need to do a little bit more work. So let's consider this further. So take, for example, suppose you want to consider the type of magmas. Then you take A of X to be just the type with a binary operation. So it will be the type of infinity magmas. And then we define tau here just by transport. You convert this equivalence into an equality and then apply normal transport. And then, of course, tau of F is an equivalence between A of X and A of Y. But what is going to be very useful is this very simple lemma, which says, suppose you have any tau whatsoever, any t whatsoever, which has the same type as tau, and moreover, t of the identity is the identity. Then this t must be tau. And now what happens in the examples of interest is that working with tau is a nightmare because you get what people call the transport hell. So what you do is you actually choose the t you want. And the only thing you have to do is to prove that the t of the identity is the identity. So here is an example which is not written in the slide. Suppose you want to prove that the type of infinity magmas is injective, yeah? And so you say, well, what should the t be? Well, the t should be a kind of transporting the group, the magma operation to the other type. And so that's what you do, the t. So you do that instead of doing transport using the transport function, you transport the the magma structure manually, and then you can easily prove the compatibility condition. So then this becomes trivial. The compatibility condition becomes trivial to check. I need to do a little bit more, which is the next lemma. This also works with sigma, but in the examples we use pi. So suppose you have any proposition P, any element P0 of P, and any function from P to U, then of course you have an equivalence like this, because if this is true for all P, then in particular it's true for P of 0. And now in the other direction, if it's true for P of 0, well, because P is a proposition, it's true for any P is equal to P. And so you get this equivalence like this. And so you can reformulate the compatibility condition using T rather than tau, rather than transport function. And well, shall I read this or not? So given A of, so this will be, think concretely, for example, using magmas. So this is well, we have a binary operation on the product, then we have a binary operation on each component, and then you want this to have a section. So if you have a binary operation in each component, you get a binary operation in the product, which is true because the product of magmas is a magma point with the pointwise operations. And that will be the same for monoids, for groups, and for lots of things like that. And so the condition is very easy to check. And the only art of this is to choose a suitable T, but your experience as a mathematician will tell you what the T has to be. Yeah, so you have to transport the operations. And if you have, for example, monoids, so you have the binary operation, but you also have the axioms. Now transporting the axioms actually is easy as well. But you have to do it, but it's easy. So you just have to choose a suitable T with this, and that's how it works. And that's basically my talk. So I finished in 45 minutes rather than 1 hour. I hope I didn't do it very quickly, but maybe I want to spend a little time discussing a few things. So I was originally interested in injectivity, well, for several reasons. First, in the last millennium when I was doing domain theory, but more recently, where more recently means 10 years ago, I was looking at searchable types, which topologically actually correspond to compact types in some models, like Johnston's topological topos. And then I started to use extension properties a lot to construct new searchable types. And what I wanted to do is to show that there are plenty of them. And I also wanted to show that they're very complicated. So I was using ordinals to measure the complexity. And so then I got sidetracked by the extension problem, and then temporarily stopped thinking about this, and then it started thinking about injectivity. Unfortunately, this work, and although it is younger than the injectivity, this one is still not published, but it's all formalized in my repository type topology. One interesting thing is that I wanted, for computational purposes, I wanted these types to be totally separated, which is the opposite of the property that the injective types have, which means that they have plenty of functions into the Booleans to the extent that they separate the points. So it's a little bit funny that the injective types have the opposite property, but they were very useful to construct types with this property. So it's a little bit surprising. Now, coming back to injectivity, so we talk about algebraic flabbiness. So you have data rather than property. But once you have data, you may want to consider some equations between this data, yeah? And it turns out that you can make algebraic flabbiness even more algebraic by considering these equations. And in fact, it turns out that then you get an equivalence. Well, I don't know if, for the moment, I don't know equivalence, but I can translate back and forth now at the moment between algebras of the partial map classifier monad and this algebraically flabby types with these extra things. So maybe I'll tell you just a little bit, given that we have time. How do I create a new page here? I think I press Command D. So suppose I'm going to do it with injective rather than with Flabby, but actually it has to be done with Flabby for reasons I don't know if I have time to discuss, but I'm going to illustrate it with injective types. Suppose you have D algebraically injective. Then you can extend this twice. So extend F along J, and then I can extend F along J along K. But of course, I can also extend F along the composite, and that will be this, yeah? And so this is the sort of equations that I'm talking about. But when you restrict this to algebraic flabbiness, it gets tricky because you fix the one at the end, right? So you fix this at the end. So you cannot really compose things like that, but there is a way to express that. And it turns out that the algebraic flabbiness with the equation corresponding to this one are in one-to-one correspondence with the algebras of the partial map classifier. And the reason this fails here for injective rather than Flabby is that if you have any algebraic injective structure, you can extend it in this way, but there is another way to extend it, which is you do the trick I said. So you define the join operator, and so you say, well, this is going to be the map that takes X in the fiber of J, this, yeah, and there is no reason, as far as I can see, why these two things should be always equal. I don't think they are actually, but for algebraic injectivity data that does satisfy that, yeah, then the algebraic injectivity data is in one-to-one correspondence again with the algebras of the partial map classifier monad. This looks a little bit like you know, the discussion about CAN extensions and point-wise CAN extensions. So this seems like a kind of an analog. So the validity of this equation here seems like an analog of the point-wise algebraic injectivity, if you like. And with this, I thank you and let you ask questions and discuss or give suggestions.
Okay, great. Well, thank you very much, Martin, for your talk. We can all, you know, visually applaud. And if anyone has any questions, you can just go ahead and unmute and ask.
Mm-hmm.
So I guess I'll start by saying I'm very glad that your final slide, your original final slide was there, because that was mostly what I was going to ask. But wonder if you can say a bit more about so now now that you're developing the theory of injective types, what you expect to be able to do either. I don't know if you're planning on now revisiting your work on searchable types and so on, or if you have some other thoughts. I guess the one corollary of all the things you said in the talk, right, is that so for example, these the type of groups or the type of infinity magmas has no non-trivial decidable properties, right? And that's
also
yeah.
the type of ordinals. So people previously proved the things like it's not decidable whether an element of an ordinal is a list element or not, and so on. And this says, well, nothing about ordinals is decidable.
Right.
Yes.
Okay. Yeah. That's yeah.
Yeah. So I mean, there is this connection, but at the moment, they're both negative and positive connection. So this was a negative connection, so you cannot do that. But I don't have time now to give my talk about searchable types. But in the work on searchable types, which actually I have given many times, that's why I didn't want to give it again here. The injectivity is used in a positive way to actually construct something. Yeah. And I can give you just like a gist of that. So you have this n. Unfortunately, I mentioned n infinity, and then you have a family of searchable types. Yeah. And then I wanted to extend it to an infinity, because if I could do that, I know that if I have a family of searchable types indexed by a searchable type, which n infinity is, then the sum is searchable. And so that's why I wanted to extend it. And at the beginning, so what I told you now about the injectivity of the universe, at the beginning, I did this for this triangle, yes. But of course, it's the same formula for any map J. And but the funny thing is that the intuition was completely different. So it was an intuition, a topological intuition of getting closer and closer to infinity. And so the intuitions were different, but actually the mechanics was the same. So the formalism was the same. So this is the way the injective types were used to do this. So then if I can construct lots of them, I then in the next step, I can construct even more by doing this this step. So this kind of things, doing that. And now I can actually, this is an opportunity to comment that in some applications like this one, it doesn't matter which algebraic injectivity data you have. Because I told you that there is a left can and a right can extension. But we need this one. This one doesn't have the properties I need, right? So because the property I needed was the following. So if I have a family of searchable types, not only can I extend it to a family of types, but I want to be able to prove that for every n in n infinity, the type is searchable. And you cannot do this by cases by considering finite or infinite if you're in a computational world. And you can do this actually, but not with sigma. With sigma, it doesn't work. And so if I remind you what the extension was, so here the formula is written. So I, so that will be a searchable or compact type, and this is a proposition. I call this in the AGDA development in type topology, called this micro-Tikhonov theorem. It's a product of compact spaces indexed by a proposition. That's why macro is again compact. So it matters in this example which of the left or the right can extension you take.
Okay, yeah, that's helpful. Any other questions?
Yeah, so I had a question earlier about the like different reflective subuniverses, if it was true. Didn't you had a slide about subtypes, right?
Oh yeah, so there is a one more theorem that is not mentioned here, but is published in the 2021 paper. So if you take a subuniverse close under either pi or sigma, and I need one more condition, which I forget what it is. Then this is again injective, and this includes, for instance, the proof that the type of n types are again injective. And I suppose for modalities, if you can prove that they are either close on the pi or sigma or whatever it is,
Yeah,
one of them suffices.
right.
Then the type of model types will also be injective. But I
Can you go
haven't got,
back to that slide that was about the subtypes? I remember something.
yeah, but the subtypes is not so much about the
Right. Okay, yeah.
It does follow, actually.
maybe maybe yes, maybe you're saying is correct, because it's yeah, you can consider P as the modality maybe.
So
I don't
yeah,
know.
I thought I was thinking about this after you asked the question. So indeed it follows. You can take the map F here to be the map that sends X to the modal operator applied to X.
Yeah.
And then that satisfies the conditions 1 and 2, and so then you get that the subuniverse of model types is injective.
Yeah, that's okay, yeah.
It's a very direct proof.
Good.
And then originally whenever I saw this, I was actually thinking, is this like were you using UU here just to like aid our understanding? But then I forgot later that you show that any UV injective type is also UU injective, right? So that's
Um,
why this simplification can be made like in because I was actually looking at the formalization and I saw that we started like using UU, but that follows from that resizing thing that you showed us, right?
yes, this decomposing the constructions of 1 implies 2 and 2 implies 1. Is that what you mean? Yeah. So because if you have UV injective, then you get a UU injective.
Right. Yeah. At first I thought that was like a special
Yes.
case, but now I see that it just follows from
Yeah.
that resizing thing. So that's cool. The last thing I was gonna say was I was actually looking at the formalization and I saw that you did the H levels and this was back in 2019, right?
Mm-hmm.
So I was just gonna say I noticed in your comment you were talking about how at the time H levels started at 0, but now we could probably fix that to where we use the H levels that I just
Oh yeah, no, this is because I was lazy and I just wanted to formalize this quickly before I submitted the paper.
No, yeah, I was just saying I could
So
maybe come back.
I did something worse than Vladimir did. So Vladimir started from 0, which some people don't like, but I did it even worse. I started from 1. I called it 0. Yeah, so you're welcome to fix that, Ian. So you are familiar with type topology and this particular corner of it.
Yeah, for sure. Okay, thank you for the talk. That was great.
Yeah, thanks.
Great, yeah. Anyone else? Okay, well, I think we will thank Martin again.
Thank you.
Yeah, and we will see you back here in 2 weeks with somebody. Yeah, Jonathan Weinberger will be giving a talk about TBA. So we'll see you then.